Okay. And I just wanted to point out, and I highlighted it in red up here, that the goal is to have evidence to understand the age and the life cycle of our sun and be able to compare it to the different stages of life of other stars. We want to be able to say with certainty, yes, our star is a main sequence star. Here's how I know based on comparing it to other data with other stars. So the chart where it pegs things as either new or infant, middle-aged or adult, or dying, that's an important piece, and we've been talking about that from the beginning. Stars have a phase of life that they're in at any one time. All right, so solar mass. The reason I had you look this up is because this is the way that we compare masses of stars. Kilograms is a ridiculous unit of measure to use. One solar mass is simply the mass of our sun. It's 2 times 10 to the 30th kilograms, which is a really ridiculously huge number. So makes sense that we're going to use something easier like one solar mass. All right, onto the chart. So you had these 2 links here. The link to the doc had a whole bunch of links, and then the HR diagram, definitely a useful resource to get the color and temperature. So some of these you should have had ranges, whereas others are more specifically, it's this color or this temperature. So let's go across the visible colors of light. So I'm going to go across each of these. Notice that I can take the sun column and I can think about which of these columns does the sun best fit with in terms of characteristics. So, visible colors of light. Protostars and nebulas? None, because they are simply just gaseous balls of mostly hydrogen that are not dense enough yet to fuse. Main sequence stars, colors of light. If you open up that HR diagram, you can see they can be a lot of different colors. So I did a bunch of correcting on this in terms of, stars that are main sequence are not just going to be orange or just going to be red. I had to add in a lot of times. They can be blue, they can be white. This can be any color that shows up on the main sequence. Giants, usually red, maybe a little orange, and they can also be blue. And I wrote boo. I'm going to click and fix that. Blue. Dwarf stars, we talk a lot about white dwarfs, but you could also have a blue, a brown, a black. We relate mostly to the white dwarf because the brown and black are really dead, not just dying, but dead. A blue dwarf is very uncommon, but thought I'd throw it in there. Neutron stars, again, notice all 3 of these are under the heading of dying. Neutron stars are bright, bright white. That's because they are super hot. And then there's our sun, which on the HR is a G-class star. We know it's yellow. Okay, so if you notice, the only possible place that our sun could fit color-wise is here in a main sequence. Elements, protostars and nebulas, mostly hydrogen because they are not yet fusing, because they are not yet hot and dense enough. As you come over to main sequence stars, you can see that collection of elements, mostly hydrogen, helium, some carbon and oxygen. Again, the percentages are going to be based on how long the star has been fusing for and how close it is to the red giant phase. As you get over to the giant category, notice what's missing. There's no more hydrogen in the giant phase. Why? Because it's dying. It ran out of fuel. That's why it's a red giant. Over here under dwarfs, these are mostly carbon. A lot of times the white dwarf core is just the carbon that was the last thing that the small to average size main sequence star fused. Beyond that, it shed its outer layers. That's where any remaining hydrogen or helium would have been, but they're mostly carbon. Maybe some oxygen too, depending on how big the star was. Neutron stars are a very odd thing. They are only going to form in terms of like a supermassive star that died, and they are under such extreme pressure that any protons, electrons, neutrons in there really would have been squished and compacted into just a soup of neutrons. And if there are elements, they're heavier than iron. And then over to our sun, look what we're left with, mostly hydrogen and helium. I know that because of the chart from the previous document. about 70-ish% hydrogen, 20-something% helium. Okay, again, if you look at what our sun is, you can see where it fits and where it doesn't. And down to surface temperature. Okay, well, a nebula doesn't have a surface because it's just a blob of gas that's very spread out in space. As it condenses to become a protostar, the temperature does increase. It does start to form a surface, and you should see a pretty low temperature here. That's because it is not fusing yet, so it's not hot. Again, this is surface temperature. This is not core temperature. So main sequence stars, if you look at the HR diagram, it ranges from the red end, about 3,000, up to the blue-white end, about 30,000. That is a big range. Some of you did actually put an average number in there of 8 to 10,000. I prefer a range because it shows the wider spread. Under the giants, these are a little cooler, and I did put a note here for these guys to use red giant. On the HR diagram, they're around the 3 to 5,000 degree range. Some can be a little hotter, but most of them are condensed into that zone. Again, on the HR diagram, if you look at where the dots are, they're mostly around the 10 to 25,000 degree range, so pretty hot. And neutron stars are not on the HR diagram because they are too hot. Around 600,000 Kelvin, they can be upwards of 1,000,000 Kelvin. And then here's our sun, around 6,000 Kelvin. Again, if you look at the HR diagram, the sun plots right at that roughly 6,000 K mark, and it's a G-class star, meaning yellow. And then once again, if you go back and look, where does it fit the best with? Should be pretty obvious. And then here's your solar masses. You can see at the bottom, our sun is 1. This neutron star mass is usually around 1.4. There's a weird mathematical limit for how dense and how massive stars can be. If you're interested, you can look that up, neutron star mass limit. These guys, the white dwarfs, can range, but they usually are pretty small. They could get up to 1.4, but I think 1.2 is the most massive white dwarf that was ever identified. So they're pretty tiny, which we knew that. Red giants, I know that they are big in terms of taking up space, but they're not very massive. They've swelled up. So 0.5 to 5. Some of you had, I think, like 1 to 10 solar masses. That's okay as well. The idea is that they should be less than 10 solar masses. And then you can see, again, a huge range of masses for main sequence stars. There is a lower limit. 0.08 is actually a lower limit. If you have a mass of a star that is less than 0.08, it's not actually a star yet. It's probably a protostar. There's not enough mass for it to fuse, which means it can't be a star yet. And then upper limit-wise, you can actually have massive main sequence stars, upwards of 200 solar masses, but they're not super common and they die really fast because they burn their fuel really fast. So really, this is an appropriate limit from about 0.1 up to about 50 solar masses. Again, it's a huge range because main sequence stars can be a huge range of temperatures and colors and therefore sizes. So looking at the diagram, again, the goal would be to be able to use the data to prove what kind of star our sun is. And here's our sun compared to all the others. And I think it turns into something that's fairly obvious once you have it all laid out in this form. And then this bottom question, again, this was for you guys, just food for thought. There are the 3 main ages of stars. Are they newly forming? Are they middle or adult aged? Or are they dying? And in thinking about the ages and the other qualities, the data that you see here, the percent of hydrogen remaining from the other assignment, you've got a lot of information to relate to. This is all going to be super important when it comes time to think about the summative assessment. So that's something that's going to be posted on Wednesday, the 25th. And again, my expectation and my hope is that you've got all 3 of these assignments done, 3, 2, and assignment number 1, and that you've got a really good bank of information to pull from relating to the sun and life cycle of all stars and thinking about the fate of our sun. What will it become when it starts to run out of hydrogen? So that is all I've got, and that was quite a bit. But do your work, ask the questions, keep pushing through, and I'm here if and when you need me. And hopefully, you guys will be doing awesome on the summative.